So I come back and I'm sorry about that. So now let's look at functions. So you've seen one kind of way of defining functions. So those are actually mathematical functions or symbolic functions, because there what you're doing is you're defining a variable, right, and then defining a function like this. This is not a programming function, it's a symbolic or mathematical function. So here what I mean by function is, you have we have seen some kinds of control flow. One is a control statement, if else. Another is loops, by which you can do something many times, not one thing but different thing each time, right? Now suppose you want to do one thing repeatedly, not in a particular order or not iteratively. You want to do one procedure several times in different places. You have already been doing this, because here what you are doing, creating a graph from a matrix, for example, or making a standard graph or getting its adjacency matrix and so on. So all these are functions. These are library functions. So now you want to do something new on your own. So we have to define our own function, that is custom function. Again, in any programming language this will be there. So in Python or in Sage, how you define a custom function is using the def keyword, def for define, and then the name of the function. So you can call it f, or here I can say, for example, double. Okay, double is not a good idea. dbl. This is for giving me the doubling some number. Okay, this is a very simple function, unnecessary function, because I can always do 2 into this one. But let me write it for showing a very simple example. So double of x. So this should give me the value 2 into x. So the keyword for giving back the value is return. Again, very common in many languages. Return twice x, 2 into x. So as I said before, the colon for creating the block, and inside the indentation for keeping the block. So whatever you write with the indentation is a function, and after that it's not. So see, when you have the return keyword, Python or Sage already knows that this is the end of the function. So that's why here if I press enter, it is indenting it. So if I do something else like x equal to 1 or something necessary, it will keep the indentation. But don't do this. It will keep the indentation. Whereas after the statement, when I press enter, it is already coming out of the block, because that's the end of the function. So return should be usually the last statement of your function, because after that whatever is there won't be executed. There are other situations where return itself occurs inside some if block or something. That's a different case. But simply if you have return in the function somewhere like this, after that whatever is there won't be inside or won't be executed. Okay, so now come outside the block and let's see if it works. So print double of, yeah, okay. So this is, as I said, very simple unnecessary function, and this is also mathematical. This is just a normal f of x equal to 2x. So why is this needed? Why is this complicated definition needed? Because here you can do more that you can't do there. What you cannot do with mathematical functions, you can do here, because here inside this you can have any programming construct like if or while or so on. So let me try this. In fact, I'll create a new cell and do it. Okay, so I want to sum all the numbers, all the integers between a and b. It's also a simple example, but this is not a simple mathematical function. If you know the formula for this, of course you can write it as a formula. you can figure out the formula for the sum of the arithmetic progression from A to B with common difference 1, and then write that. But suppose you don't know it, or suppose it's more complicated. Obviously, if you can do this, then you can do more complicated things also, right? So you can sum cubes of functions or cubes of integers and so on. So for everything, you may not know the formula. So I'll start with a simple one and make it more complicated. Imagine you don't know the formula. So you want to find the sum of all the integers between A and B. How to do this? So sum is equal to, I won't use sum, it's a keyword, s is equal to 0. Now for k in range A comma B plus 1. Why B plus 1? Because the range of AB will give me A plus 1 etc. up to B minus 1. Right, so I want B also. So range A B plus 1. Okay. In this, S plus equal to K. So K takes values from A to B plus 1, A to B rather, one after the other. Each time that I take that value and add it to S. S is already defined here as 0 to start with. So now in this loop, I am adding K to S each time. Is this fine? The logic is clear? Yeah. Can you? Yeah, sorry, I forgot that. Okay. Yes. Sorry about that. Okay, so fine. This logic is clear here. So return. I don't want to see. Okay. Is this correct? You have to tell me whether it's correct as written. Yeah. What is it? Indentation. So this currently is inside the block of the for loop. So this will try to return the value in each iteration, but even that's not correct, because in the first iteration, as soon as return is encountered, it will immediately stop. It will go back from the function. So what this will do as written is take S equal to S plus A. So S will become A and immediately it will return. First iteration itself will return. So I want to return outside the for loop. So let's check it with something we know. 1 to 10 if you sum, the sum should be, you know the formula, n into n plus 1 by 2. Right? So this should be 55. Is it working for everyone? So you can change this also. So you can do it even minus 10 to 10. Correct. Minus 10 to 10, if you sum, you should get 0. So there is no limitation on A and B. Can be any this, but A has to be greater than, A has to be smaller than B. I should check this. Is a bad way of checking. Yeah. Here. Okay, fine. Okay. So if I try to sum from 10 to A to B such that A is greater than B, it's giving me 0. First of all, let me say why it is. Why? Because here you have range of A comma B plus 1. Okay, so in this range function, if you give the first one greater than the second one, that range will be an empty list. Range is a list, remember. Let me show you that. So So if I say range of 1 comma 11, this is 1 to 10. This is a list, right? What if I give 11 comma 1? That's an empty list, because from 11 up to 1 there's nothing, right? It's not going up. There are different ways to get descending list and all that, but that's not the basic thing. So this will be empty. That is a problem. So if I want to, one way is I can validate it here, as I said, if A is greater than B, then what should I do? Okay, print is one option. Print that A should be, yeah, fine. A should be less than B. Okay. Exit or return? I don't think there is exit. Oh no, okay. Oh, that's because I said print. It's not exit, it's return. I have to restart. No, restarted. Yeah, only the kernel exited. So it'll restart. So don't use exit. Exit will actually exit the kernel. So in Sage, when you are running notebook, each notebook has something called a kernel, which is where all the processing takes place. It is not in the browser that the calculation is taking place. This thing you are running, I have minimized it here. Yeah, this thing which you are running, this is the server, right? Notebook server. In that, the computation takes place. But for each notebook, you have a separate kernel. Even if you use Mathematica, there also there is a kernel for Mathematica. So each notebook has a separate kernel, because in the kernel the variables, everything will be stored. So if you are using a different notebook at the same time for some other purpose, so you are working on graphs in one notebook, matrices in another notebook, or groups in another notebook. So G is a graph here, G is a group there, but there is no conflict because the kernels are different. Okay, one will not override the other. So each time you start a notebook, here one kernel will be started. So sometimes when you have errors, one thing you can try, when it's not at all working, one thing you can try is restarting the kernel from here. Okay, don't try it now because it will take a long time. So one thing to try is restarting the kernel. Similarly, you can, when you do close and halt here, it will stop the kernel, and then save the notebook first, close and halt. It will stop the kernel and then close the notebook. Otherwise, if you close, the kernel is still running. Okay, fine. So here I hope that it has started again by now. We'll just evaluate, but first evaluation takes a little time. Yeah, so if you do this here, this is one way to handle the error or invalid input. Print A should be less than B and return. Okay, so that works. Only here you will see none. That's because I'm printing the output, but in case of error, the output is not there. So it should not give me anything. Okay. There is another way to throw errors. So I'll show you that. Yeah, but I want you to modify this while this is validating. I want you to modify this function so that it will give me, are you listening? Modify the function so that instead of just summing integers from A to B, it will sum powers of integers from A to B. So that should be another option here. Okay, P, where P stands for power or N or whatever. So that I want to get A to the power P plus A plus 1 to the power P, etc. instead of just A plus B, A plus etc. P. So modify it by taking a third argument P, which will be used for computing the sum of the powers of integers between A and B. So please try. Alright, I didn't think. So okay, let me go back to this. So yeah, I want powers, p powers of the integers. So what will I? How will I modify this? Very small modification. What is required? S plus equal to, see, k is the number, a and so on. So k raised to p. Yes. Here I should change it. So 1 to 10. So for example, let me see squares. Okay. Yeah, 385. That you can check. How do you check? Its formula is n into n plus 1 into 2n plus 1 divided by 6, which is correct. Okay. So it's more general. So this is the advantage of functions. You can have very general functions which will do this for you. So if you want just sum of integers, you can use it. Now you can use it with p equal to 1. Yeah, maybe not record, but let me show you a nice thing. Here, suppose I just want, normally I want sum of the integers without any power. So that is normally I want p equal to 1. So every time right now what I have to do, I have to give 1 here. But most frequently, suppose this is my use. I don't want squares and cubes and all that. This is my most frequent use. Occasionally I want to find sum with other powers. So for convenience, what I can do is make this third argument a default argument. So I can say p is equal to 1. So p is equal to 1 is the default value of p. So if I don't supply this argument, it will not give me an error now saying the number of arguments is less. It will say that it will give me the answer with p equal to 1. Right. Whereas I still have the option, if I give another power, that will also work. I can also explicitly say p is equal to 2. That's also an option which you have been doing in all the graph plotting and those functions. You have been using that. Like when you say that legend is so and so, there you are using this actually. So if you are not using I said this earlier, you can give arguments in different order if you use the names. But if you are not using names, then you have to keep the order. So A and B, we are not using names here, 1, 10. So that has to be in the correct order. So I cannot put this p equal to 2 first. Okay. But if I do this, this is fine. I can do this also. But for the convenience of being able to write in different order, I have to write every name. Right. So this will be convenient if you have a function with several arguments, all of which are optional or most of which are optional. Like plot functions, there are so many possible arguments there, legend, vertex, the point, everything, so many options are there. So you can't remember the order. So what you can do there is remember the names or get the names from the documentation and specify the ones which you want, so that the order doesn't matter. Whereas for simple functions like this one, it's easier to remember the order. First of all, because there is a logical order in the arguments. So the lower limit to upper limit is the most natural order. So if I say 1 to 10, that's very easy to remember. I don't have to spend extra effort for that. Right? Okay. So inside functions, you can have if, for, and other function calls also. So you can call other functions from within this. You already done that anyway, because k power p, it's an operator. Operators are basically functions. So inside one function, you can call another function, not define another function. That's also there. You can define two functions and call one from the other. That's always possible. Now for this one, I wanted to see whether there's another possibility. Raised, right? Okay. Yeah, I'm not sure about this, so I won't go into this. But yeah, printing is not the good way of throwing errors. You should actually, what you should do when you are writing a function for other people also to use, or for yourself to use in the future, the errors should be of this type. It should not be printed as an output. When there is an error, the execution should stop there, and it should return report an error like this in this format. So there are ways for that. I'm not going to that now. I don't remember, but there are ways to do that. So printing is not the best option. Of course, here I don't need to raise an error. Okay, I can just do it in the opposite order. So what will I do if suppose A is actually greater than B? What do I need to do? Swap them. You have shown the function. Okay, so for swapping, usually in the other languages, what you need to do is use a temporary variable. So C is storing the value of A, then A is replaced by B, then B is replaced by C, and so on. Right. Another option is that plus and minus trick. A plus equal to B, and so on. So here you don't need that in Python. You can do AB is equal to B comma A. Okay, this will swap the values. It looks counterintuitive, but it works like this. You already seen multiple assignments. A comma B equal to 2 comma 3. If I do, A will be 2, B is equal to 3. Here I am using that same thing, but for swapping. So now it works. So yeah, let me just show you. Fine. Let me, before proceeding further, let me show you how to use this interact, right, which I said is very useful. So now that we know how to define functions, interact is, firstly, you need this special type of keyword at interact, at the rate of interact. Okay, and then in that cell you need to define a function. It can have any name, but we are not going to call that function from anything else. This interact thing is there, this widget will be using that function, so we don't need to call the function. So I don't want to waste a name on that function, so I'll use some name which I'm sure I will not use again, which is something like underscore. Underscore is a valid function name. Okay, so I'll use underscore here since I don't want to use it anywhere else. So normally if you see interact examples, they will be named like this. Now in this I want some kind of way of specifying parameters. So for example, order of a graph. So n is the order of the graph. This I want this to be a slider from say 3 to 10. So I can create a cycle graph. Okay. So n equal to 3 to 10. So n is just like the argument to the function, but with this option. So 3 comma 10. This tuple specifies a slider from 3 to 10, going 3, 4, etc. Now inside the function, g is equal to say cycle graph of n, and g don't show. That's it. Basic syntax is only this much. By default, the slider will be, when you first evaluate, the slider will be positioned in the middle value. You can change it to any of the smaller or larger values. Each time you change, the function will be run again with that particular value. Okay. So this is just a way of, so normally what you would do like this is, if you didn't have this interact functionality, what you would do is what? Define a function once and then you will write this in a separate cell, right? So you would have a cell here which is calling that function with say 5 and evaluate it, right? And then you will have to come here and manually change it to say some 7, like this. So interact is doing exactly that, but with partially with the graphical interface. So the slider is provided to you, so you don't have to manually type and change it. It's there, right? Again, I'll change the fixed size so it's visible. Okay. If you click this, it becomes blue, and you can change it with the arrow keys also with the keyboard, like this instead of the mouse. You can drag it with the mouse or use the arrow key once you click it. Okay. Now I can have, this need not be a single argument function, I can have multiple parameters. So I have m is equal to say 0 to 45, because 45 is the maximum possible number of edges with 10 vertices, 10 is my maximum number of vertices. So instead of cycle graph, I'll create random GNM with n vertices and m edges. So it's evaluating. Now you get 2 sliders. Okay. It's taking time. Yeah, fine. So there are 2 sliders, you can change them independently. Yeah. Right. Again, if I change it and change it back, I'll get another random graph because this is random. So 8 itself, I want another graph. I can do this, just change it back. But there is a better way. Also, so now you have seen 8. Suppose you want 12 edges. What you have to do? Drag this to 12. But you see what is happening. It is going through all the values through which I dragged it. I don't want that, especially if I am working with larger graphs. I don't want it to spend time constructing those graphs and compute. Maybe instead of just showing the graph is not of much use, I want to compute something with it. So something like g dot spectrum. Okay. So it is showing me the graph and then showing me the spectrum of the graph. So when I go to this, each time it has to generate the graph, then compute the spectrum, which is not very efficient, right? So I don't want this. I want to be able to change the slider to whatever I want and then generate that graph. So did you understand till here? This basic thing you got working? Is it working for everyone? Okay, so I'll show you how to make this stop giving me all the values in between while I change the slider. So for that, I'll to the function add just one more parameter, which is auto underscore update equals false. By default it's true, that's why this is happening. So if I make it false, then you get this button, run interact. So now if I change it to say 10 and yeah, changes to 17, it does not change the graph. So if I click run interact, then it does. Okay, so this is more efficient because it does not spend time computing everything in between. Okay. So this is a very useful tool. As I said, when you're doing some research and you want to check several cases of a particular kind, you can do this. Is this fine for everyone? Okay. So, like graphs, another very useful construct is a matrix. And you must be knowing in MATLAB how you can work with matrices. In Sage also we can do that. So to create a matrix, so far you have learned how to create a list. So if I do 1, 2, 3, this is a list, not a matrix. Okay, if I try to multiply this, say, this doesn't work because these are lists, not matrices. So what I want to do is multiply matrices, right? So to create a matrix, list is the basic thing, but I need a function. Just like you need graph function for creating graph, here you need matrix function for creating a matrix. So the format is this. You need a matrix, the argument to the matrix function is a list of rows of the matrix. So list is what? Square bracket, open close, right? In this, you need to specify the rows. Every row is again a list. So for example, 1, 2 is one row. Rows are the same size obviously. 3, 4 is another row here, and 5, 6 is another row. Okay, this is a matrix. And as usual, I can see it like this. So if I say A, or equivalently print A. So this is not the best way of displaying it, as you know. So how will you display it better? Show of A. And now suppose B is equal to matrix. So if I want a vector, again I have to specify it like this. So I want a column vector. So the first row is say -1 and second row is +1. So this is B. So I can show A, B, this is a list, A, B and A into B. Okay, I'm showing 3 matrices in a list. So A, B, A into B. So this star is now a matrix operation, not arithmetic operation. So all the other operations on matrices are also there. So I can do 2 into A, scalar multiplication of a matrix. That is there. If I have a square matrix, I can square it also, or take powers, any power. So let me say that P is equal to, so how will I get a square matrix from A? I can do, for example, A dot transpose times A. Transpose of A is A dot transpose. It's a function, so open close bracket. And I can square or cube this. So I'll look at P cube. So this is the matrix P, which is actually A transpose A, and this is its cube. I hope this is working for everyone. You can also have complex matrices. So say C is equal to matrix of. Did you introduce complex numbers? So you know complex number, imaginary root of -1 is capital I, right? So I want a matrix of this form, say 1 plus I, then 3, then 2 minus 3I, okay, and I minus 6. Yeah, this is a complex matrix. So of course you can do C dot transpose. But normally when you have complex matrices, you don't use transpose. You use the Hermitian transpose or conjugate transpose. So C dot conjugate transpose. You can guess that it's there. So when you tab complete, it's there. Of course, you can just conjugate it also. Again, normally you don't use that. So conjugate transpose or Hermitian transpose is this. Yes, as you can see, it is. This is the transpose. This is the conjugate transpose. Now, what are some other things you can do with matrices? Inverse, right? So, in fact, let me invert this complex matrix itself. That is taking time. I hope it's not singular. It's even difficult to check because it's complex. No, it's not. Yeah, here's inverse. So whether it's real or complex, you'll get the inverse if it's non-singular. So yeah, maybe before the inverse, more basic one is determinant. So yeah, determinant is 4 and that is 3. You can write det or determinant. This is also there. Same thing. Just det is also fine. Okay. Yeah, this is what. Instead of transpose, there's a shortcut. That is capital T. Okay, instead of writing the full transpose, this is capital T without any open close bracket. Just C dot capital T. That is the same thing. And I guess this is there. I have to check though. Oh no, that's not there. My mistake. Conjugate transpose is the full thing you have to type. Anyway, it's not, you're not typing, it's tab completion. So if you have used MATLAB, you know you can solve systems of equations by either you can find A inverse and then multiply, or you can do left division. Right? So A inverse x, rather A inverse B is nothing but A left division B, because you're multiplying A inverse on the left. So suppose I define A is equal to some coefficient matrix, say 1 0 1 0 1 0 1 minus 1 and minus 1 1 2, and B is equal to say 2 0 2. Okay, this is my unknown vector. This is not wrong. This is not correct, because I need this column vector, right? Of course, a cleverer way of doing this is writing a row vector and taking transpose. If you want a column vector, easier way to, for writing, it is easier to write a row vector and take transpose, because so many brackets you don't have to write. But anyway, to be clear, I'll write this. So what I want is to solve the system. So let me see what the system is. So I'll show A comma B. So it is a system with this as coefficient matrix, this A is coefficient matrix, and this is the unknown, rather this is the right hand side. So what I want is A inverse into B. I can do left division. Yeah, and that is correct. You can easily verify that 1 1 1 is a solution. So this is the same in MATLAB, same syntax in MATLAB. So now another very common matrix thing is eigenvalues and eigenvectors. So again, let me say that A is for example, let me take a graph matrix, just for example. So graph start cycle graph of 5 dot or 6 is better. 6 dot adjacency. This I will have to type. Yeah. So this is my adjacency matrix. Whatever, you can take any matrix you want, any square matrix. Now, eigenvalues, one way I told you is directly from the graph you can do G dot spectrum. But this is an example for matrices. So suppose you have a matrix from somewhere. Here, just for example, I have taken a graph, but you have some matrix from somewhere. Naturally, you can find its eigenvalues using the matrix dot eigenvalues. So A dot eigenvalues. So for example, print or show. Okay. This is C6, so these are the eigenvalues. But you also have eigenvectors, right? So if you do eigenmatrix, okay, this will give you the set of eigenvectors. So this is in fact in MATLAB, for example, what you would write for this is, say for example in MATLAB, you would write this as x comma v is equal to eigen of a, right? So what does this give you? It gives you the, in MATLAB it will give you the set of eigenvalues in the form of a diagonal matrix whose diagonal entries are eigenvalues, and the eigenvectors as a matrix whose columns are the eigenvectors. Here it is giving you the same thing. Only the command is our function is a dot eigenmatrix right. This because if you take an asymmetric, this is symmetric, but if you take an asymmetric matrix, left and right eigenvectors will be different in general, right? So I could have taken something else. Here is I'll take this, but okay. Yeah, I didn't show you the incidence matrix earlier. So let me take the incidence matrix. Okay. So normally incidence matrix is rectangular, but this is a cycle, so number of vertices, number of edges, so therefore it happens to be square. Yeah, but it's obviously not symmetric. Okay. So yeah, just to take a different example, I've taken the incidence matrix of the cycle. You can see its eigenvalues are rectangular. 2 is of course an eigenvalue because row sums are all 2. Okay, even columns are 2. Yeah, so here the displays the modern kernel. Firstly, because I've zoomed in, so probably in your computer it may be better. That's because these irrational numbers are being shown with several decimal places. Okay, if I take a smaller matrix, say, let's say I take 3 by 3 for now. Right, that's much better. The problem is it's symmetric. Yeah, this is even better. Yes. You can see that the left and right eigenvectors are different. So there is some symmetry here, but they are not exactly the same. In general, you can expect very different left and right eigenvectors. Singular value. Is there a singular value decomposition? What is it? Okay, let me before that show you some more ways of creating matrices. SVT of. Oh, okay. Okay, all capital. Oh no, this is the matrix space problem. Okay, that's fine. It's okay. I'll take up this later. Yeah, let me see. Let me show you different ways of creating matrices. Um, Now we have a 4 by 4 matrix A, and let's say B is another 4 by 4 matrix. Again, to quickly generate a matrix, I'll take some graph matrix. Three, yeah. You can take anything you want. So A is a 4x4 matrix, B is a 5x5 matrix. I can make a block diagonal matrix with A and B as the diagonal blocks. So say M is equal to this. Yes. This is a quick way of making larger matrices if you have some block structure. And of course, I can make normal block matrices also. If you have 4 different matrices, you can make block matrices of this kind. So suppose that instead of these zeros, I want something else here. So I've just created a matrix C, and now I'll say that is equal to the block matrix in which the first block row is A and C. I can see that C is of the correct size, I think. And the second row, if I take C transpose, it will be the correct size. So C transpose and then B. Yes. So instead of block diagonal, you can also create other general block matrices. So now this is A, C, C transpose, and B. Okay. Again, you can check other things like eigenvalues and all this. So I will quickly compute it. This is a very large matrix, it's 9 by 9, right? So we have so many and they're all irrational. And even complex eigenvalues are there because it's not a symmetric matrix. So you can expect complex eigenvalues. So in graphs, we have seen the adjacency and Laplacian matrix. What I left is the incidence matrix. So G is equal to, let's take the simple, okay, let me take a random graph as well. Let me take a random graph with 6 vertices and say 8 edges. Yeah, this is one of the random graphs. Now, if you want the 0 1 incidence matrix, you do G dot incidence matrix. Is this okay? This is the 0 1 incidence matrix. But you also have some other incidence matrix with this, which is the 0 1 minus 1 incidence matrix or oriented incidence matrix. Right. So to generate that, again the function is the same, but here you specified oriented equals true. So it will give some random orientation and then generate the matrix. You are not seeing the orientation here. You will just give a random orientation and then no, not B. Normally it is called Q. So I'll call it Q. Yes. So this is with some random orientation. The only difference is if you refer to the usual books like Professor Bappett's book, in that the convention is the source vertex or the tail vertex of the edge is given +1 and the head vertex is given -1. Terminal vertex is given -1. Here the convention is the opposite. -1 for the source, +1 for the terminal. But that doesn't change any of the theory. Only the convention is different. All the theory about rank and all those things are same. You can just adjust it with the sign. Because if you want the other one, you can always, if you insist on getting the same thing, you can always make it minus. You can do it with that, but you have to remember. So it doesn't matter actually. So theory remains the same, so you can always use this with the Sage convention. And you can verify whether this is correct. So rank of Q, for example, rank is another matrix function on Q dot rank. Q is a matrix, so Q dot rank is indeed 5. For a connected graph, the rank should be, it's a connected graph, the rank should be n-1 for the oriented incidence matrix. So yes, it is. Again, you can find its eigenvectors and all those things. So eigenvectors, right? Oh no, this is not a square matrix, so you can't do that. What I want is the nullity eigenvector. Yeah, these of course. This, column space. Yes. Right. However, this is not being, because it's an integer matrix, it's not being treated as a matrix over the reals, it's treated as an integer matrix. So you're getting the column space as a module overrunning, okay, over the integer ring. You can always change that. Yeah. So those are further options. So tomorrow we'll be seeing. Yeah, so we'll wind up now. And these are just the basics, so that tomorrow we can show you how to write some solid programs. Okay, combining all of this.